Okay, so we are given an equation that gives us the displacement of a wave in relation to position and time. X is in meters, time is in seconds. We're tasked with finding the frequency, the wavelength, and the velocity. To determine frequency, we're going to set x equal to 1. We're going to take our string, for example, and study only one position on it in relation to time. And what that does is it eliminates one entire variable so that we can graph it. We're going to get something like this. Our displacement goes up and down in amplitudes of 3.5 centimeters. At this one position on our string, it takes from time t2 to t1 to go one full wavelength. Here we have t2, here we have t1. 1 over delta t, which is the time required to go one full wavelength, is 20 hertz. For our second part, we're going to solve for wavelength. We're going to study all of the string at one time. So we're going to basically just look at the wave. Here we have x2 and x1. That's one full wavelength. And I would say this is a snapshot of our string. We'll put meters here. x2 minus x1 is delta x, and that is equal to lambda, and that gives us a distance of 2.3 meters. So I'm going to put 20 hertz as our frequency and 2.3 meters as our wavelength. Now, we're going to solve for our wave speed. We're going to take our familiar equation, frequency equals velocity over wavelength, and just move that around algebraically so that we solve for velocity. We plug in our known frequency and our known wavelength to get velocity. We have 2.3 meters times 20 seconds to the -1 power, and we get 46 meters per second. Zoom in on the answer. We're left with our answer of 20 hertz as our frequency, 2.3 meters as our wavelength, and 46 meters per second as our velocity.